Hi, everybody. Today what we're going to talk about as we walk through this lesson is we're just going to do a quick little algebra review. And so what I want to throw out is a large number of areas we're going to cover in terms of just a quick kind of knock the rust off, let's get back into the swing of things sort of review. We're not going to touch on everything. We've still got a couple more days where we're going to kind of get our feet back used to doing this. But we're going to hit off a lot of areas today. And so your mentality going into today's lesson is, I know this stuff. It's maybe been a while since I've seen this stuff. We're just going to work our way through, as I said, to knock off some rust, to get rid of some cobwebs, get back into the swing of things. Okay, what you see on their screen right now, there's our first simplification question. So you see the instruction. I'd like you to go through and simplify. Now, considering this is all review, I want you to tackle each one of these problems on your own first. So this becomes an opportunity for you to go through and pause the video, attempt the problem yourself, then we can unpause it and we can kind of catch up and see where we went. Okay? So I want you to give the solution to problem right now. Pause it now. Okay, and we're back. So the way that we've walked through this in the past may differ, kind of depending on your pathway through. But I'm going to just put on what simplifying 3 root 12 may have looked like for you in the past. So, as an example, we maybe looked at that root 12 and looked at the 12 specifically and said, if I can factor that 12, then I may be able to do my root operation, my square root, to part of that 12. And maybe then we noticed that we could factor 12 into a 4 times 3. And if I just focus on my root, I'll notice that I have like a little bedmass situation. I have one term, and what makes up that term is my square root, which would act like repeated division, and I have my multiplication in there. That means that to take the square root of that one term, I can take the square root of it in its parts. And so maybe we were required to write down this line in the past, taking the square root of the individual factors, and then calculating your root 4 because you can, but not calculating your root 3 because you can't. That's an irrational number. We would be forced to round it off. And therefore, you could simplify that first radical into 6 root 3. So hopefully when we reduced or tried to simplify that expression, we did simplify the first radical to 6 root 3. I just want us to know that we can get there in a much more direct fashion. So I'm going to erase everything you see there. And I think, and I'm hoping, that maybe we've used factor trees or something along the lines that enables us to go through and reduce that radical in one step and one step only. So what I like to do, and this is just preference, is I like to do a little factor tree. I'm going to kind of squeeze it in there and fit that in on that line because when I do factor 12, I can factor that into a 4 and a 3. And I can see within that line what I need to factor. So for me to go through, I have the 3 out in front. I look at my factors that are underneath and I say, I can take the square root of that 4, so I do it. Square root of 4 is 2. Collect that with, or simplify that with, the coefficient 3, so there's my 6. And what is left underneath the root? Well, I can't calculate the square root of 3, so I leave that underneath, and we go one line and one line only. So hopefully that's an approach that we can use to be able to go through and reduce a radical quickly. So my goal then, if I'm going to use my little factor tree, is to try to factor 18 in the next radical into values that I can take the square root of. So preferably perfect squares. So I recognize that I can factor 18 into 9 times 2. And I can take the square root of that 9. I like that, so that's what I do. The square root of 9 is 3. I simplify that with my 5, so there's 15. And I can't take the square root of the 2, so that operation is left. Now, I'm just going to hop off to the side for a second, because this is why I like my factor trees. That I didn't have to go through and factor that into 9 times 2. Now, ideally, I factored it into 9 times 2 because 9 was a large perfect square. However, maybe when I see 18, I automatically factor that into 6 times 3. Well, I notice that I can't take the square root of either of those values, so all I do is just extend my factor tree if possible. Well, I can factor 6 further into 3 times 2. And now I can see that I can reduce that radical. When I take a look at that, I have 2 3s underneath that root sign. And so really what taking the square root means is find 2 of the same factor. Well, I just found 2 of the same factor. And so I can then go through and I can take the square root of the 2 3s, which is 1 3, and the only factor in there that didn't have a partner to it, that didn't have a pair, was that 2, then it would be left underneath my radical. And you notice that if you were to go through now and reduce that radical and simplify it with a coefficient of 5, we're going to get down to the same thing. There's our 15. So that's why I like to use factor trees, because I never have to be perfect when I factor. Now, ideally, I want to push myself. That since that number is underneath a root sign, I want to try to reduce it as fast as I can. So take a look at the next radical. I see root 75. Ideally, I want to break that apart into 25 and 3, because I can take the square root of 25, which is 5, but I can't take the square root of 3. I think the next one provides a really good case for us trying to be as efficient as we can be. I would have a number of people that when they see 48, they automatically go to like 6 and 8. If we were to do a factoring question, 2 numbers multiplied to give 48, I think a lot of people would choose 6 and 8. We can just see that there's nothing wrong with that. It just means that we can't take the square root of those and their bits, and so it means then we need a little extra work to be able to work our way through and say, okay, well then 3 and 2 and maybe 4 and 2, and we're good. We do have a perfect square, so we can end that branch. We also have 2 2s, and if I have 2 of the same factor, then I can take the square root of that. And so it just makes our factor tree about as complex as what it would be. So the focus that I want you to have in your mind is to say, okay, when I factor something, because that number is underneath the root, I have a purpose. And that purpose is to look for perfect squares. So maybe we think that this one's really good. And we go 4 and 12, because I can take the square root of 4. But we've got to look back at the first radical and the problem I gave you to see that, yeah, like root 12 isn't simplified either. And so if we were then to go through one more step and maybe factor 12 into 4 and 3, well, now we can see that we've got our 2 4s, and we can take the square root of 2 4s because that gives us 1 4. That maybe we even ideally see that when we see 48 underneath a root, the best way to factor 48 is 16 and 3, because we can take the square root of 16, and that is the biggest square root. 3 cannot be factored further. So when I go through and I see 48 underneath there, I want to factor it into 16 and 3, because the square root of 16 is 4. Multiply that by 2 to give me my 8. I can't take the square root of 3, and we're good. Now that we have that purple line and all those radicals are reduced, now we can just go through and we can put together everything. So I can see my like radicals. I have a 6 root 3 minus a 5 root 3 plus an 8 root 3. So that's going to give me a 9 root 3, and I can't collect it with my root 2. There's your final expression, and we're good. Okay, so as I said, hopefully we're knocking off the rust. I would love it if your background had you working with factor trees like this, or any other method that you have that enables you to reduce a radical in one line. Okay, let's jump into the next problem. Okay, you take a look at problem B. We have a nice binomial, all squared. So we have our perfect square, and the base of that square is a binomial. So, same as the last one, what I want you to do is I want you to go through and simplify that expression. So, you're going to simplify it on your own. Pause the video now. Okay, we're back. And so, what I'd like to do is just throw up the fact that this problem that I just gave you is no different than the red problem you now see on your screen. It's a binomial squared. And I just want us to see how consistent we were with our approach. And make sure that we did not try to simplify that expression by just squaring both terms in the base. And for anybody who said, oh, no, but it should have been a plus, that's just as incorrect. That we should know that when we go through and we expand a perfect square binomial, then we square the first term, we multiply those two terms together and double it, and we square the last. Because when we have multiple terms in the base, we have to expand the brackets. We can't square the individual terms. So just take a look back at what you attempted when you went through to square B, and make sure that we didn't make a common mistake. I think for anybody that went through and actually went, okay, well, I know that my squared means that I would have another one of those, and then you just went through and you expanded your brackets, like I think I'd write boo on your page for doing that. However, at least we recognize that we do have to expand. So let's try to take an approach through B that would be consistent with what we would deal with, a binomial squared. Okay, I want you to repause the video and go through and make any adjustments you need to make through to be able to simplify that expression. Okay, pause it now. Okay, and if we're back, then I want to walk through what I think should be some minimum steps for you to be able to go through and expand that. I want to talk a little bit about approach, because if we were to go through and expand that perfect square binomial on the right, we would say that we need to square the first term. So we got to square the x. So I need to square my 5 root 3. I would have a lot of people that would want to write this down. And I'm just going to shy away from that, because I think that although correct, it's not the best way to think about the problem. That I'm hoping that when we look and we see that we have 5 root 3 squared, we can tell the difference between the red and the purple. In the red, I have 2 terms in my base. In the purple, I just have 1. And so to square my 1 term, I square all parts of it. We can see the 25, and I'd really love it if we weren't trying to picture root 3 squared as root 3 times root 3. That when you think of it as root 3 times root 3, we then think of it as multiplying radicals, which leads us to root 9, which then requires us to reduce. We should be very good to go from root 3 squared immediately to 3, because we know that a square and a square root are opposite operations. Those cancel out. And so the more we can start to think of root 3 squared as just 3, and the number 9 never comes into our head, then I think the better off we will be. So I'm just going to get rid of all that gold on the side. I'm going to re-put in that first term. And now what I want to do is I just want to adjust that purple. That I think a great first line for us is that. Okay, I got to square my 5 root 3, so I square my 5, 25, I square my root 3, 3. Okay, now we come to the middle term. The middle term is going to take a little bit more work. If we look back up into our red, we know that we have to take the x and the 3 and multiply them together, and then we double it. We know that because we're going to get a negative 3x and then another negative 3x term when we expand. So we're going to do the same thing in the purple. Multiply your two terms together. 5 times 2, 10. Root 3 times root 6, root 18. Now double it. There's the correct term. It's just unsimplified. So I think we should be able to do all of that in one go. The same way as in the red, we deal with it in one go. Okay, multiply your 3 and your x together. So there's a 3x, double it, 6x. Let's do the same thing here. I'm just going to switch the point in which I double. 5 times 2 is 10, double it is 20. Root 3 times root 6 is root 18, double it, root 36. And hopefully you just caught my mistake. But it is easily the most common mistake you can make in this instance. I'm going to go back and I'm just going to kind of walk through what we just had there. We actually had 5 root 3 times 2 root 6, and we see that that is going to be a 10 root 18. If I ask you to double that, that would be the same thing as adding on another 10 root 18. And we should all be good that if I take 10 of something and add on another 10 of something, then I have 20 of that something. That my coefficient on the radical changes, not what's underneath the radical. And so maybe now we can really see where I made that mistake on that root 36. That should have still just been a root 18. Okay, I'm going to get rid of all that gold. And we're getting close to having this one in a really useful form. Back up on the red, we would now square the last term. So I square my 3, negative 3, and I get a positive 9. Now I have to do the same thing in the purple, but I'm a little bit better now when I do it. I square my 2, there's my 4, square my root 6, 6. And there we go. I think you guys should really like that line for 2 reasons. I'm going to go pretty quickly. 25 times 3 is 75, and if I jump down to the end, 4 times 6 is 24. The only thing left for me to do now is to reduce my radical. So I have my 18. Well, that can be broken up into 9 and 2. I can take the square root of 9. That's a 3. Multiply that by my 20. What can't I take the square root of? 2. And now we can just collect like terms. My whole numbers will collect to 99, and I cannot simplify that with my root 2, and there we go. Okay, hopefully not too bad. Some people can go from that original expression right onto that line. I just don't know if I'd recommend it. I think you might be risking a little too much in terms of mistake. Okay, there's a full review for us in terms of radical operations. So we should be pretty comfortable to get back into the swing of working with radicals. Now let's change directions a little bit and let's get back into some notation. So what you see on the screen, you should be copying that down into your notes. There's our first problem. We've got if, yes, that's my cursive if f of x equals x cubed plus 3x squared minus 2x plus 3, then I'd like you to find both a and b. Now, I'm not talking about this problem or taking up your time with this problem because I think you really need it. Like, there is something important about the fact that we have some function notation here, and you're enrolled in a class called Advanced Functions, that this is going to be a very predominant, or this will be a predominant notation that we're going to use. But it's really about what would you need to show me if I ever asked you a question like this. Now, I need to be clear that I would never put a question like this on an evaluation. It is too basic. It's grade 11 content. But what work do you need to show, and what would I recommend as we start to do small parts of this, or this action, as small parts of other problems. You take a look at A, and we should be reminded that our function was f of x. It's a function that is called f, and it is made up of x's. And so when I see the notation f of -1, that's telling me that I replaced my x with a -1. I need to replace all my x's with a -1. And so I think a good step for us is to make the substitution and then simplify each power. So there's a -1. -1 squared is 1 times 3. -2 times -1. Add on my 3. So that gets me a 6, 8, and it sums up to 7. If I was to ever give you this as a problem, and I told you I won't, but in terms of notation and what you would need to show me, I would hope that we could all understand that if somebody just said equals 7, we could see where that comes from. That you would never have to show me that line. You can, because it's going to help you to avoid mistake, but it would never be required as part of your solution. Okay, why did I spend time on B? Just to remind us that also we can make a substitution of an expression, not just a constant. We can sub in variables as well. Now, the other reason why I wanted to talk about B is because a lot of people would make this common mistake. 2x squared, there's my 2x squared multiplied by 6x squared. And hopefully you can catch my mistakes in that line. There's something in us, I think, at times, and maybe it comes from power laws a little bit, where when we see 2x cubed, we get really focused about applying that cube to the variable, but we also forget to apply it to the coefficient. It always seems to be a coefficient mistake if anyone makes one. So let's make sure that we're good, that first case would be 2x cubed, so that's a 2 cubed, and then my x cubed. In the middle term, or I should say that next term, I'm going to take a 2x squared and square it, so there's a 4x squared, now triple it. And if you came in on that, then I think we're doing great and we've knocked off enough rust on our function notation. Okay, let's change gears again. So now I want to work our way through just some simplifying and get back into the swing of working through some algebra. So there's 2 problems that you see up on the screen, and I want you to tackle both of these problems in one go. So on one pause, I want you to work your way through both. We've already reviewed a little bit that will help you with A. That one shouldn't cause us too many problems. Work your way through B. That one gets a little uglier. Perhaps that one might take a little more time. Okay, I want you to work your way through and simplify both those expressions. Pause the video now. Okay, we're back. So really the only reason I told you to tackle A was it gives us a chance to just make sure that we knocked off enough rust and now we're back into the swing of dealing with perfect square binomials. Okay, I want us to take a look at B, because one of the reasons, or the main reason why I wanted to talk about B, is we're going to get into a bunch of instances where we have a binomial times another binomial. And coming out of grade 11, that wouldn't have been like advanced algebra, but you should have looked at it more as like, okay, so it's just a pain. So you might give me this green solution where we just like put the blinders on and we just truck through that algebra. And so maybe what we do is we expand the first 2 binomials. There's your 12x squared. My middle term is going to have a -8 plus a 3. And now when you expand that, we just have to multiply in our next binomial. So it just becomes time consuming. And then So the fact that we are taking 3 terms and we are now multiplying it by 2 terms, it shouldn't surprise us that we get 6 terms. So there's a 48x squared minus a 20, sorry, that's a cubed, x squared minus 8x. Now I jump into my purple terms, if you want to think of it that way, minus a 12x squared plus a 5x plus a 2. So it just takes time to crank out those 6 terms. Well, now we go ahead and we collect. I got nothing to collect with my cubes. I have a couple x squared terms. I have a couple x terms and my constant. So we get down to that point, and hopefully your solution matches up with mine. Okay. The reason I wanted to talk about B was to get us over the fear, maybe, of a binomial times a binomial times a binomial, but also to have us start to kind of take the blinders off a little bit. That there could have been a more efficient solution for us to get in this case. And perhaps, and I'm hoping, that maybe we saw those 2 terms and we recognized that there was a pattern to it. Hopefully we recognize those terms as conjugates, and we know that when we expand conjugates, 2 terms that have different signs in between, that we're going to get a difference of squares. And so since that original expression you see in white was just something times something times something, my only operation is multiply. Well, it doesn't matter what order I want to multiply that in. That what I'm going to do is I'm going to multiply the 2 starred terms first. Because when I expand that, that just gives me a difference of squares that is only 2 terms. And my background has me being very efficient at being able to expand a binomial times a binomial. And so now when I expand that, there's my 48x cubed, my minus 32x squared, my 3x, my positive. And you guys might really like that red solution better. So by just taking a moment at the beginning, 3 seconds, 5 seconds at the beginning, it might allow you to become a lot faster with your work, but also avoid some mistakes in there. So something to keep in mind as we move forward. Okay, let's throw up one more. Question C is just going to act as a problem for us to just really make sure that we can kind of consolidate what we've talked about. So I want you to go as fast as you can through C. Simplify that expression. Pause the video now. Okay, we're back. So I shouldn't have to slow down on this. We should be pretty quick. That first binomial expanded. Our only mistake is going to be if we tried to multiply that 2 in before we address the exponent. Right? BEDMAS is going to tell me that I have to deal with that exponent before I deal with multiply. There's our good old grade 6 theory, BEDMAS. So we got to make sure that we pass grade 6. And so I'm going to maybe leave that 2 out in front and expand. Some people will be quite comfortable to expand the perfect square. Okay, so square the x squared. Now multiply that by negative 2. Put the 5 and the x together, there's a negative 5x. Double it, negative 10x. Multiply it by negative 2. Square the 5 is 25. Multiply it by negative. And they may go straight from that line to that line. You use up whatever space you need to be comfortable with it, with a little bit of pressure on you to try to work to be a little more efficient, a little better than what you were the last time. And hopefully we get down to that and everything matches up and we're good. So we hopefully now have a ton of rust knocked off on dealing with simplifying radicals, a little bit of function notation, a little bit of expanding, some simplifying with some algebra. Okay, let's go the opposite direction. What you see in your instruction in 4 is we're going to go back and do a very, very fast factoring review. And I mean it will be very fast. There's going to be no concern on your part if this factoring doesn't go so hot today. I'm going to go through it very quickly, but we're going to have our own dedicated day to factoring coming up, like tomorrow. So as we're working our way through, if I'm going a little too quick and it's not coming back to you, don't worry about it. As I said, we're going to spend a whole day talking about it. However, I want to maybe lay the groundwork for what we should be comfortable in factoring with. So let's take a look at A and B. I want you to go through and factor both. Pause the video now. Okay, we're back. So most people should have been able to look at A and say, hey, there's my trinomial that takes a special sort of pattern, a squared something, a single something, constant. And therefore, we were saying two numbers that multiply to give 12 and add to give -8. There's my -6 and a -2, and there we go. Okay, we jump in and we take a look at B, and we notice we've got the same pattern. 3 terms, I got a squared something, I got a single something, I got a constant. However, the difference is I have a complex trinomial because my leading coefficient is not 1. And so whatever fast factoring method you use, I just want you to be comfortable to be able to factor that in one step. So for me, I'm going to hop off to the side. I'm going to do a little fast factoring. I've got 2 numbers that multiply to give 2, 2 numbers that multiply to give 3. I go through and multiply into the other brackets. There's a 6 and a 1. I can get a 5 out of that. I'm just going to get rid of those green arrows. I can get a 5 out of that if my 6 is positive, so there's a positive 6 and a -1, and I do get a little confirmation that a negative times a positive gives me a negative. The only thing left for me to do, put in my brackets and my variables. 2x minus 1 times 1x plus 3, and I know that we're never going to write that 1 in there for form, and there we go. So, as I said, you may not use that same fast factoring method, but I want you to work your way through to be able to factor in one line, some form of fast factoring. If you are used to using, say, a process called decomposition, where you factor that over 2 or 3 lines, then I want you to talk with me, and we're going to spend some time going through some fast factoring. Okay, let's keep it going. What you see on the screen now, there's 3 more problems. I am making the assumption that we are all good at fast factoring because you've been doing it since grade 10. So what I want to talk about with the problems that we have on the board now is, can we work our way through and be a little more efficient at our fast factoring? So what I want to do is I want to start to limit the guess and check aspect of it. We're going to be a little better than what we were before. So I'm going to walk my way through a really long, prolonged fast factoring method. Okay, I take a look at C, and I say, I need 2 numbers that multiply to give 6, and I go 6 and 1, and 2 numbers that multiply to give 4, I go 2 and 2. So I'm going to cross multiply now. There's a 12 and a 2. Can I get an 11 out of that? Nope. So I flip them. Now, for anybody who goes, hey, flip 2 and 2. Okay, well, we got to stop and we got to look at that for a second. For anybody who goes, hey, I flipped 6 and 1. Yeah, it's not going to make any. So now what I do is I just remove one of those options and we start to change what we had. So for me to go through, maybe now what I do is I get rid of that 6 or that 2 and 2 and I go 4 and 1. Okay, I cross multiply again. 6 and 4, I can't get an 11 out of that. So that didn't work. So now what I do is I flip those. Rather than 4 and 1, I now have 1 and 4. Well, when I cross multiply on those, now I'm going to get 24 and 1. There's no way I'm going to get 11 out of that. So now I go through and I change my 3 and my 2. Or sorry, my 6 and 1 into a 3 and a 2. I now get 12 and 2. I can't get 11 out of that. So I flip them. Now, I don't care which one you flip. Flip any one you like. Maybe you want to go through and you want to flip the 4 and the 1. Now I multiply across. There's a 3 and a 2. I can get an 11. That was about as long of a process as what you could have taken in using your fast factoring. However, there are certain features in that problem that allow you to almost immediately get to the correct combination of factors. So what I want to do is I want to go back and I want to put on a scenario for us. Because I could see an awful lot of us starting off fast factoring and saying 2 numbers multiplied to give 6 would be 3 and 2, and 2 numbers multiplied to give 4, 2 and 2. And I want you to understand that there are 2 things in that factoring question that would identify for us very quickly that that is not possible. Okay, I'm going to put up both. I want to draw to your attention the first thing. My fast factoring is going to say that those would be my brackets. And I don't want you to get focused on the fact that those don't work. What I want you to imagine is that they did work. And so I wrote this down as my solution. Everybody should be able to stop and look at that and say, that is not possible. And what it requires is us going back to our factoring checklist and remembering about the look-fors that we have. The first thing we should always be looking for when we get asked to factor, is there a common factor? And so when we scan the coefficients, 6, 11, and 4, we should see that there is no common factor in that expression. Now I want you to look at your last factor. Do you notice that there's a common factor in there? And if there's a common factor within a factor, then if I was to expand all those brackets, I would have a common factor in my simplified form. You can see the common factor of 2. And because there isn't a common factor in the original, then I know that when I make up my fast factoring chart, I have to make sure that I don't put a common factor in there. So I'm just going to get rid of all that red down here. And I'm going to go back up into my chart. And I'm going to practically write this down. Okay, 2 numbers that multiply to give 6, 3 and 2. 2 numbers that multiply to give 4, 2 and 2. No, I can't put that 2 there. Because then I would have 2 even numbers. And if both those are even numbers, then they share a common factor of 2. And since there is not a common factor in the original, I can't put an even value there. There's one way to not write down an incorrect combination of factors. It allows you to avoid that right off the bat, which is nice. Okay, the second one, and this one's a little more reasoned, that I could actually talk to you in this one around grade 4, grade 5. I want you to imagine that I put down my 2 and my 2. And now I go through and I cross multiply. Well, I'm going to take the 3 and I'm going to multiply it by 2. Then I'm going to take a 2 and I'm going to multiply it by 2. Notice that I multiply both of those values by 2. I'm going to multiply both of those values by an even number. And what type of number do you always get anytime you multiply by an even number? We should recognize that you also get an even number. And so if I was to add or subtract an even number with another even number, how could I ever get an odd? I can't. And so there's another part in that original expression that tells me that I can't have 2 and 2 back there. I take a look at my middle term, my sum, and I recognize that if I make both those numbers even, there's no way I can get to that middle number. And so I never even try, never try 2 and 2. Never even comes up. So I save all the time I would have incorporated in that fast factoring. Now, maybe it's a 1 and 4 then, or I know it's a 1 and 4, but I also would never try that because now we see there's your common factor of 2. And so very quickly, and I mean with a little bit of experience on this, you're going to come in probably on that within about 10 seconds. That we can see our 8 and our 3, and we can get an 11 out of that. And very quickly then, we're just putting in our variable and our brackets. And now we have it factored. So it's something for us to be conscious about. That we do have a method to fast factor, whatever that is. But we can get better at our fast factoring by incorporating some of these numeracy concepts. So what I want you to do is, if C wasn't so fast for us, then I want you to pause the video and give D a shot again. Okay? So let's pause it now, give D another shot. Okay, we're back. So maybe I take a look at this one, and I tend to go to the middle as much as possible. Not always, but the middle. So when I look at 18 and I say two numbers multiplied to give 18, I'm conscious of 6 and 3. Now I take a look at the end and I go, okay, I've got my 20. So just to reiterate, I'm not going to make that my 4 and my 5. Because if that's my 4 and my 5, there's a common factor of 2 there, and my original expression does not have a common factor. So I am not going to write that, and I jump straight to a 5. I want that to be in purple, a 5, and a 4. So now when I multiply across, there's a 15 and a 24. Those are 9 apart. So I need to make it a -9. So my bigger number, -24, would be negative, and my 15 would be positive. And now all I need to do, put in your brackets and your variables, and you are good. Nice. Okay, we take a look down at E, and I should be able to catch up a little bit with you guys. I'm just going to make that a little smaller. That hopefully when we took a look at E, we were like, hey, I got 2 terms in there, not 3. And I recognize that there is my difference of squares. And I know that my difference of squares factors into conjugates. There we go. So hopefully that factoring review came back pretty quick. And as I said, we're going to have a whole day dedicated to factoring. Reviewing some of this stuff again, but also going quite a bit deeper. Okay, let's take a look at the last problems. Okay, so what you see up on the board now, there is a problem that should kind of go back to Unit 2 or Unit 3 in your grade 11 university course. That we should be able to simplify that expression, and we look at that, and that is just a fraction divided by another fraction, and you have been asked to simplify. I'm even going to help us out a little bit at the beginning, that this was probably one of those problems that you guys looked at as almost a puzzle last year. That in order to simplify fraction operations, what we really want to do is reduce our fractions. And therefore, we want to factor everything to see what goes into each expression. That is, this problem was probably one of those ones that you went, oh, so I just factor every expression, and then I look to cross stuff off all over the place. You work your way through. So what I'd like you to do now, let's pause the video, go through, and try to simplify that expression. Okay, pause it now. Okay, and we're back. So hopefully when we took a look at this, the factoring was pretty straightforward. Difference of squares. I have a perfect square. Now, some people will choose to write my divide and then go through and start to factor the next fraction. Now, my only concern with that is if we get a little too eager to divide out common factors, then we may start just crossing things off, and we haven't actually crossed a division operation. That is, we may choose to divide out something here with something up here, and there is no division operation between those two things. So my suggestion to you is rather than write down your division symbol blindly and then factor the second one, how about we jump in and we factor the second fraction? However, I know that to divide fractions means that I'm going to flip and multiply. Then why don't I multiply by the reciprocal right now? So I'm going to take the denominator of the second fraction, x squared plus 5x plus 6, factor that, and go straight to writing it on top. I'm going to take the numerator, x squared minus 7x plus 12, factor that, and put it right on the bottom of that second fraction. Now, everything within that expression is multiply and divide. I can see clearly what's separated by division operations. So I can go through now and start to divide out some stuff. I can reduce the first fraction. I got an x minus 3 divided by an x minus 3. And that is it. I'm going to actually bet that for a lot of people, they might have questioned themselves because they were so used to last year, so many things crossing off all over the place that everything really reduced, that because there was only one common factor, you thought you probably made a mistake. You didn't. So now let's multiply our fractions together. And there you go. Never be concerned about expanding the brackets on top. Count how many terms you're going to have on top. Take a look on top. How many terms do I have right now? I have one term. This whole expression is one term because expressions are separated by, terms are separated by addition and subtraction. That is a big multiply symbol in here. Same thing on the bottom. So for me to go through and expand my brackets, collect like terms, I'm not going to be able to reduce that fraction at all. I am done. The only thing I had to remember, tack on your good old restrictions. I know that x cannot equal 3, 4, or negative 2 to have that expression be the same value as its original expression. Okay, there we go. Hopefully not too bad. Okay, I'm going to leave you with the last one. You take a look at B, and I'd like you to go start to finish. Okay, this is a good old grade 5 question. You're going to go through and you're going to subtract two fractions. So I want you to be able to subtract two fractions. Pause the video now, give it a shot. Okay, we're back. So for us to go through, then the first thing we want to do is we want to factor that denominator because we want to see what makes up that denominator. Do the same thing on the second fraction. What makes up that denominator? Because now we can see that our common denominator has to have the factors from the first denominator and the factors from the second denominator. We can see our whole denominator in there. There's my first denominator. I can see it. My second denominator requires an a minus 6 and an a minus 4. Well, I have an a minus 6 and an a minus 4. If you blindly went through and multiplied both of those denominators together, there's nothing wrong with that. You now have a common denominator. We just have to be very careful that we don't create a problem we don't have the means to solve. If you just multiply your denominators together, then you may end up creating an equation, a fraction, that you have the ability to deal with, but what you will guarantee is that it will reduce. In this instance, we were able to get a lower common denominator, and because we were able to find that lower common denominator, I may get to avoid reducing. So I'm just going to get rid of all those green and yellow underlines. And now we're kind of playing that game of what did you do to the bottom, do the same thing to the top. So to take that first denominator and now look at the whole denominator, what was different between the original and my new one? That a minus 4, so I need to make sure that I multiply my old top by a minus 4. What was different in this denominator and the whole denominator. I got that a minus 3 factor, so I need to make sure that I take my old top and I multiply it by a minus 3. Okay, now you take a look on top of that red fraction and you notice that you have two terms. Two terms can simplify. So I'm going to go through and I'm going to expand. A lot of people will skip that step because they're not going to fall into the trap of that negative on their last term. That they'll expand the a's and then subtract them. They'll get a negative 3a and a negative 2a and a negative 5a, subtract them. They'll get a positive 6, subtract it. And they'll go straight to that line. Now we notice we can collect like terms on top. My a squareds are going to cancel out. I can simplify my a's, and I love what just popped up. Because now we can take a peek and we notice that this fraction can reduce further. I have an a minus 6 factor on top and I have an a minus 6 factor on the bottom, so I can reduce my fraction. Just as sometimes when you add or subtract fractions together, you can take your answer and reduce further. We get down to that expression, as long as we tack on our restrictions that a cannot equal 3, 4, or 6, and I think we are doing outstanding. So if you were able to work your way down to that, then I think we have got so much rust knocked off, like we are rid of cobwebs. We're good to start jumping back in. If we struggled through a little bit today, then your goal is going to be, oh, okay, I remember this stuff. I'm just rusty with it. I'll get there. I'm going to work hard to get there. If there seems to be some bigger kind of issues of, I don't even remember tackling that stuff. You did. It just might take a little extra effort and you reaching out to me to make sure that we can get kind of back into the swing of things and get back into the shape of working through this stuff. Okay, your job, jump in and get some practice. Get as much practice as you can or reach out to me with some questions and we should be good. Okay, good luck.